חברים, שמח לארח אתכם, ובעיקר שאתם מוכנים לארח את ניר, ובעיקר שניר מוכן לתת לנו הרצאה, שאני בטוח שתהיה מרתקת. קהל קטן אבל מאוחר. דוקטור ניר באט למד את תואר ראשון ושני בבן גוריון, אצל ידידנו במדבר יוסי חצור, ועם ניר סגי פה, היום זה פה, אני לא יודע מה זה היה פה, כן, מעבר לגדר, במכון הגיאולוגי. נסע לאוניברסיטת בראון ועשה שם תואר שלישי אצל טליס וגרג היל. הוא עבר באותה הזדמנות מנושאים של חספוס, שהוא עסק בהם בתואר השני, לנושאים שהיום מדבר עליהם, על הקשר בין טמפרטורה וחיכוך, מה שנקרא thermal pressurization. היום הוא באוניברסיטה של פנסילבניה עם דויד קוצבי, ועובד על סקלות יותר קטנות, רמת העכביש, אבל עדיין בנושאי חיכוך. ניר, בבקשה.
Okay. Let's see. Oh, it's working. Okay. Good morning, everyone. Thank you all for coming. Thank you for the opportunity to speak in front of you. And thank you for the introduction, Amots. I'm going to talk to you about some of the work I've done during my PhD at Brown University on the activation and arrest of thermal pressurization in localized faults. So let's start off. Yes, got it. Okay, let's start off by talking about fault zones and specifically about the big problem that we're trying to solve here. So we can categorize fault zones, and I want to underline the word zone because maybe we're used to thinking about faults maybe in the lab or from maps as small lines or very small features, but they are big features. They include many geological structures, a lot of variability in terms of the thermal structure of the rocks, the rheology, and the hydraulic structures. And that's what makes them such interesting phenomena to study. And we can categorize fault zones into basically two types. The localized faults, where we have almost all of the deformation localized along a very narrow zone, and then this fault core, which is made up of highly deformed, fine-grained materials, and it's surrounded by a fractured rock. It's a damaged zone, and the number of fractures decreases as we move away from the fault core. On the other hand, we have our wide fault zones, and they are much more complex. They have more dispersed deformation, multiple cores surrounded by multiple damage zones, and a highly intricate structure. So we're going to talk about the first type. It's easier, but it also poses a lot of problems in earth science. And the main problem, before that, let's just take a look at how these faults look at the field scale. As I said, these are very enormous geological phenomena. You can see here from the Atacama Desert in northern Chile, we have a fault core zone. I highlighted with these red lines the individual fault cores. You can see through the texture and just from the color of the rocks that they are different from the damage zone. And just look at the scale here, and this is a very, very large fault. What we want to deal with is these narrow, localized fault zones. And this is an example from Southern California. The Punchbowl Fault has been studied extensively in the past 20 or 30 years. We have our country rock over here and over here, our fault core in these black cataclysite layer. And within that cataclysite, there's the principal slip surface where almost all of the deformation or almost all of the slip motion along this fault has localized upon. And I highlighted the principal slip surface. And if you take a closer look with this photomicrograph, you can see that the principal slip surface here is highly localized, surrounded by some textured cataclysite. And what's truly amazing about these types of faults is that the degree of localization is so intense that basically we can get so much deformation along such a very narrow zone. And this fault displaced a total of 45 kilometers of slip. And it's just an incredible thing to think about, that so much displacement can occur in such a small scale. Moving on, maybe the biggest problem that we have with these localized fault zones is that they have the potential to generate copious amounts of heat. And if we just do this simple back of the envelope calculation, we'll take just an anonymous fault at 2 kilometers depth. We have the overburden pressure from the rocks above. We have just solving this simple heat equation, where we only have a heat source and a diffusional term. And for this fault, if we use very basic coefficient of friction of 0.6, which is true and good for crustal rocks like granites, seismic slip velocity of 1 meter per second, and a coefficient of thermal diffusivity that is good for these types of rocks. We let our anonymous fault slip, and after 1 second of slip, the fault surface temperature reaches almost the temperature of the surface of the sun. So obviously, this is not true. Otherwise, if this were true, we would see widespread melting around our fault zones, our exhumed fault zones. And another problem that poses is that if we cause these widespread melting, and these are very high temperatures, then once these melted rocks cool down, they would actually pose as seismic barriers. It will prevent that specific fault patch from slipping again. And we know that fault patches slip over and over through some seismic cycle over the years. So if you're not convinced by this, I'll just show you some supporting evidence for why we don't see any widespread meltings, which suggest that coefficient of friction is actually low. Just because all the parameters I input into this model are you have to trust me on this, are true parameters, but the coefficient of friction is probably the least constrained parameter what we have from earthquakes and our knowledge from seismic inversions. Okay, first line of evidence is that frictional melts are scarce in exhumed fault zones. And we study exhumed fault zones because they are accessible to us. We can look at these seismogenic faults that produced earthquakes in the past, and if you're a very good field geologist, you can see wide range of features within that environment. But these types of features, like these pseudotacholites or partial melts, are hard to find, and that is of two reasons. I put here an asterisk here because either these faults just don't generate them because they're just not getting hot enough, so we're not getting these partial melts, or they're just underrepresented within the rock record. And what I mean is that you can look at the scale here. This is, I think, a €1 coin. These are very small features. You have to be a very skilled geologist to find these small-scale pseudotacholites. And moreover, that these pseudotacholites are prone to chemical alterations. We're looking for these types of faults, or the field geologists are looking for these types of rocks and exhumed conditions. They have been exposed to meteoric waters, and they've been at ambient atmospheric pressure for quite a while, so they are not stable at these conditions. So the second line of evidence is that earthquakes can rupture through potentially frictionally stable patches on faults. And you may have seen this before or may have not. I'll just go really quickly about it. When we do friction experiments in the lab, we can do experiments where we slide at a certain velocity, v naught. If we change the velocity by a step function to a new higher velocity, v, we either see that the coefficient of friction of our experimental fault would either, the steady state coefficient of friction would either increase relative to the initial coefficient of friction, and this is called velocity strengthening, meaning as we go, as the material slides faster, it's harder to push to push the rocks past each other, and this is a stable frictional regime. It's hard to propagate an earthquake through such materials, let alone it's basically impossible to nucleate an earthquake in these types of materials. On the other hand, we have the velocity weakening behavior, which is frictionally unstable. It's easier to propagate earthquakes, and this is the condition that we need to, at least from what our current research shows us, is these types of materials that actually generate earthquakes. So we need the velocity strengthening material to nucleate an earthquake and make it bigger. Whereas an earthquake that ruptures through a velocity strengthening material it wouldn't be energetically favorable to make it larger and larger. But what we see is that earthquakes can rupture through these frictionally stable zones. The top 2 kilometers of the Earth are basically usually filled with more loose sediments and clays that fill up the fault zones, and these materials are velocity strengthening materials. So it's hard to propagate an earthquake within them, to make an earthquake larger. What we see, and this is an example from the 2011 Tohoku Oki earthquakes from eastern Japan, that the earthquake itself ruptured through all the way to the bottom of the ocean. So it ruptured through all those loose sediments and clays that are frictionally stable, that show this frictionally stable behavior. So something had to occur to make an earthquake, so the coefficient of friction had to be small in order to let the earthquake propagate all the way to the surface. And the fact that it propagated all the way to the surface and caused the ocean bottom displacements, vertical displacements, is what caused the devastating tsunami that ensued after the earthquake and caused so much damage and loss of life. So last 2 points I want to talk about is that there is a known absence of heat flow anomaly across fault zones. So if fault zones generate heat, if the coefficient of friction is high, and we generate a lot of heat along faults, we don't see those. We don't see any heat signature when we do surface measurements. It's not the heat flow when we cross a fault discontinuity is not higher or significantly higher than the background heat flow from the Earth itself. So that points out that the coefficient of friction that is low, and these faults are actually weak. And again, from the Tohoku Oki earthquake, the residual temperature anomaly measured after the earthquake points out to a very low coefficient of friction, less than 0.1. This is true also for the San Andreas fault. This is true also for the huge 2008 Wenchuan earthquake in southern China, in Sichuan, China. And we also know that water is present in all seismogenic fault zones. So go deep enough in the earth where we start to generate these earthquakes, there's water or fluids like brines that are just within the pore space of these fault zones. And that changes and makes the whole picture a bit more complex. Okay, so it's been for the past, I guess, 40 years, 50 years, people have been doing these friction experiments in rocks. And they show that when we slide, so this is steady state friction versus the slip rates in meters per second. When we slide slow, we have a pretty high coefficient of friction, 0.8, 0.7. When we start sliding fast, coefficient of friction drops. And people were looking for answers why that happens. And some of these, they have proposed that when we slide fast, we're starting to activate dynamical frictional weakening mechanisms. And some of them have been proposed before any experimental proof was given. Some of them were shown through experiments and then modeled later. And probably the most prominent one is flash heating. I'm not going to go into it, but it has been shown theoretically and corroborated through lab experiments. But other ones have been only theorized. For example, acoustic fluidization. I put a T there for theory, and thermal pressurization was the other one. And there is reason to believe that thermal pressurization is it's a very important weakening mechanism in earthquakes. So first of all, I just want to talk to you about what is thermal pressurization and to get a better understanding of what the processes that are involved. Let's take our anonymous fault. Here we have some country rock in white. We have a gouge layer or just rock where deformation is localized, so we need to generate a lot of heat. And we have water within the pore space and within the cracks in the fault, and along the principal slip surface or any surface or any shear bands that occur within this localized fault core. And we have normal stress acting on the fault, and we know that the shear stress is just a function of the coefficient of friction, the normal stress, and the pore pressure. And if we have water present, there's some pressure. And when we start sliding this fault at slip rate V, we start to generate heat. And the heat, as we slide faster, we generate more and more heat. Or if we slide under higher normal stress, we generate more heat. And we see that when we heat up the rock, we also heat up the fluids within the pore space. Because the thermal expansivity of the fluid far exceeds that of the rock and the pore space itself, the fluids are going to start to pressurize within the pores and along the discontinuities in the fault zone. And if the slip event is fast, seconds, it's going to be we're going to basically trap our pore pressure, our elevated pore pressures, and the heat within the fault zone. It's because if we take longer it takes more time to diffuse away these excess temperatures and pore pressures. So at effectively undrained conditions, pore pressure is just going to build up more and more, causing P to increase and the shear stress to drop, leading to sliding at very low heat generation capabilities. So we have a mechanism to slide with almost no shear stress and little heat generation. That's preventing melting of the entire fault zone. Here are some equations for a model from Jim Rice from 2006. This is a 1D where the x dimension grows at the direction normal to the fault plane. The fault plane is here, so normal to the fault plane. It takes into account the properties of the rocks and the gouge around the fault zone. We have these coupled PDEs, temperature evolution equation. We have a heating term, a source term, and a diffusional term. And the same for the pore pressure evolution. We have a source term and a diffusional term. And I just want to stop for a minute and talk about this parameter, capital lambda. Capital lambda, you can think of it as kind of like a pore elastic parameter. It ties the thermal response of the faults to the elastic response. You can think of it as it has units of stress per degree C or temperature. And basically, if lambda equals 1 MPa per degree C, that means that per unit increase in temperature, we're going to pressurize 1 MPa of pore fluid. And that's basically what drives pore pressure up. So Rice makes some assumptions. He solves for a fault with no thickness. He assumes that the other parameters are constant. He can get an analytical solution for the shear stress, for the temperature rise, and it depends on the length scale, where it's a function of the pressurization factor and the thermal and hydraulic diffusivities. And as you can see through Rice's model, it's beautiful. It's a beautiful work. We have shear stress, we have fault slip or fault displacement, and the temperature. They're normalized by their initial temperature. And shear stress drops considerably, so there's almost about 80% weakening by the time I stop this model. And you can see the temperature rise, the buffering of the temperature rise, where we have thermal pressurization and when we don't have thermal pressurization. So we have a means to stop the temperature rise. We're pretty happy. We have faults. It seems reasonable to occur within fault zones because the permeability and the diffusivity for fluid is pretty low. Heat is effectively trapped at these time scales. So we're pretty happy and we can move forward. Why we think that thermal pressurization is important for earthquakes and may be important for almost all earthquakes is through this plot from Vieska and Garagash from 2015. They included the Rice's TP model within their earthquake rupture simulation, and they calculated the emitted fracture energy from their simulation, and they found out that when they have thermal pressurization, then they can explain the observed fracture energy from real seismic events. These are all real seismic events, or fracture energies from real seismic events. Using only the TP model, they can explain all these observations from very small earthquakes, 4.4, up to subduction zone earthquakes of magnitude 8 and more. And this is really truly amazing. And kind of tells you that thermal pressurization may be dominant in almost all earthquakes, from small to big ones. Furthermore, thermal pressurization has been identified and studied in other processes which involves fluids, heat generation, such as landslides. Any mass flows may have thermal pressurization activated, and also in meteor impacts where there's any fluids present. It doesn't really have to be water. It can be any type of fluid that can pressurize. And so there's a big, wide range of phenomena that we are interested that thermal pressurization may be important in. So moving on to our experiments. We use a rotary shear apparatus to test thermal pressurization, and you can see that rotary shear, if you haven't seen one or haven't heard about this type of instrument to test friction, we basically have a top rock ring or sample and a bottom sample. They don't have to be rings. This instrument, it does. Some other apparatuses just use solid cylinders. They can slide to an infinite displacement where both rings just displace one relative to the other about the axial direction, and but the whole setup sits within the pressure vessel, so we can do everything within conditions that mimic or are close to what we see in the Earth, where earthquakes occur at 2 kilometers depths and more. And that is probably the most powerful thing about this apparatus is that we can do these experiments at these high pressure conditions. And I'm not going to go into the nitty-gritty details of the apparatus. We can talk about that later if you want. The sample assembly itself consists of a bottom sample grip made of steel. We have our rock here in blue, which is epoxied to these wells within these sample grips. And we have the top sample grip here with the top sample. Our fault is down here. And we can, maybe you can see this from this lighting. We can supply pore pressure through these pore pressure ports through a separate pore pressure intensifier system. We basically control pore pressure here and here. We know that the samples are saturated when we just have flow from one end to the other, where we measure we have our measurements. And the whole thing sits within the pressure vessel, so confining gas pressure from compressed nitrogen of 45 MPAs, normal stress of 50 MPAs, and pore pressures of 25 MPAs. And 25 MPAs is a number I just want to touch on for a second here. If we go lower than that, less than 20 MPAs, if we increase temperatures to the water boiling temperature, we are at risk of going through the phase transformation of water from liquid state to a gaseous state. That adds another layer of complexity to the experiment. Some experiments have shown this before, that they can heat up and get that gaseous state. It's hard to get a lot of knowing what happens after we go past this transformation. It's almost impossible to continue to pressurize more fluid once we reach a gaseous state. So we just like to keep our pore pressures at 25, so we always have a liquid state in our experiments. We never go fast enough that we go into supercritical fluid for our water, so no problems there. And this jacket is basically made out of Teflon rings and rubber O-rings, which isolate the fault itself, here, from the surrounding nitrogen gas. So we use Frederick diabase as our testing material, and there's three reasons why we use this diabase. Diabase, I think, usually is called dolerite from European and maybe Israeli researchers. Americans like diabase. It's a mafic. It's a mafic intrusive rock. Usually, you can find them in sills. And first of all, it's fine-grained, homogeneous, isotropic, and has a very, very low permeability, natural permeability. The natural permeability is so low, it's off this scale. It's about 10 to the negative 24 meters squared. The permeability goes into the diffusivity, so high permeability, high diffusivity, fluid diffusivity, and vice versa. And as I told you, we want to pressurize water within our fault zone. We have to have low permeability in order to keep those pore pressures within the timescales of our experiment. So it's a homogeneous rock, low permeability, and we can control the permeability through the heat treatment, where we just put the samples in a furnace at ambient pressure, and when we heat it up for a certain temperature and for a certain duration, we propagate cracks through subcritical crack growth, and we can change the permeability of the rock. And the last thing I want to tell you is that because of the low silicon content of the rock, we are not activating any other frictional weakening mechanisms that have been shown, like silica gel formation. Rocks that have, like granites that have higher silica content, some amorphous silica gel can form on the surface and really cause a significant dynamic weakening. And that's another reason why we chose this rock, so we don't need to deal with activating other weakening mechanisms that would complicate our experiments even further. Okay, so this plot shows you the permeability versus effective confining pressure for diabase. I would call this the gray sample as the high permeability. It's still very low permeability, but in our experiments, it's the highest permeability that we tested, intermediate, and low permeability. Let's start off by looking at dry experiments, just to make sure that we are not activating any other weakening mechanism like flash heating. And our experiments are pretty simple. It's simple velocity step experiments, sliding slow at 3 microns per second, reaching some constant or close to a steady state coefficient of friction. We increase the velocity to 2.5 millimeters per second for about 10 to 20 seconds. Then we drop it back to 3 microns per second. And so here's the coefficient of friction in black. At 0, that's when we start our velocity step. We increase the velocity up. And over here, by 20 seconds, where the shaded area stops, is where we drop the velocity down. We also measure the fault normal displacement in microns. So this is a measure of the opening and the closing of the fault itself. So negative values are opening, dilation, where the two samples separate from each other, or open up, they never really separate. And positive values are when we just compress them even further. And you can see here from this experiment, we increase velocity, we have an increase in coefficient of friction. Okay, so this is the natural behavior of this rock, velocity strengthening, no dynamic weakening mechanisms there. Let's start adding water. And this is our high permeability sample. We start sliding fast. There's an increase, a transient increase in friction, followed by a little bit of decrease afterwards. This is 2.5 millimeters per second. Some dilation, only 11% weakening from this peak. Okay, starting to see something there. Moving on to intermediate permeability, so about 10 times lower, and getting, again, this instantaneous peak in friction, followed by about 40% weakening of the shear stress, or the coefficient of friction. It's just shear stress over normal stress. And dilation. The rate of weakening and the dilation increases as the permeability decreases. Moving on to even lower permeability, we have even more weakening, 52% weakening, and more dilation. The rate of dilation also increases. But as you can see, that these experiments show that we get these big drops in friction, but they are very short-lived. We can't maintain thermal pressurization throughout our experiments. And over here, it's only like 1.5 seconds, or 1 second. Before that, it was 1.5 seconds, 2 seconds of weakening. Afterwards, we're still at low coefficient of friction values, but we're regaining some of the strength of the fault afterwards. So we're causing dynamic weakening. If you're not convinced that it's through an increase of pore pressure that is what causes these weakening, let's look at the next slide. Hopefully I can convince you that it is. If we compare the reload response of the fault after we resume slow sliding rates, 3 microns per second, this is the intermediate permeability, this is the low permeability. It takes us about 200 seconds to regain the strength or the initial strength that we got from the fault. Whereas for the low permeability sample, it's a little bit more complex behavior, but it takes us about 10 times much, 15 times as much to regain some higher level of coefficient of friction. And still, we can't go back to the initial coefficient of friction that we had before. This really tells us that if we pressurize water fluids on the fault, in the fault zone over here, it takes us much longer to diffuse it away from the low permeability sample. So it's a signal that we pressurized pore fluid pressure during our experiments. And that's what caused dynamic weakening. And these are, in fact, the first direct evidence of thermal pressurization in laboratory conditions. There are other experiments that showed these behaviors, but they were great works, but some of them did not look specifically at thermal pressurization, or they had these problems with phase transitions. They did these experiments at low pressures or without any pressures at all. So it makes them a bit harder to say something specifically on thermal pressurization, except it existed or not. So these are the first direct evidence for thermal pressurization. And when we do these sequential TP episodes, these sequential velocity steps, you can see here, this is the first velocity step here. It's kind of hard to see because they're all squished together because of the time scale here. So we have our first velocity step and the first weakening event, 43% weakening. Then here, the second weakening event, second velocity step, the third one. You can see that their magnitude decreases as we do them in sequence. It's not only their magnitude, it's the duration for each event. They become shorter and shorter. This tells us that it's becoming harder and harder for the fall to pressurize fluid and for longer durations. And the reason for that is that we're starting to open up cracks. So the same cracks that we needed before to saturate these samples to increase permeability. Yes, to increase the permeability, opened up during our experiments, and we can see that through this. Stress diagram. This more semicircles. This is at before sliding the semicircle. Here's the stress conditions on the fault. As pore pressure increases, the semicircles become smaller and move to the left. So we're starting to induce these tensile stresses within our fault, and this is basically due to our experimental geometry of the fault. So when we look at our fault zones, these are our rocks. This is the fault itself. All those small cracks, you can see them better over here, are starting to open up through these tensile fractures, tensile stresses that open up and help diffuse away some of these pore pressures around the fault. So it really tells us that pore pressures, we can't build them up for longer durations because we're just changing our surrounding rocks during a TP event. Okay, what about wider faults? I'm still talking about localized ones, but ones that we have some gouge. We just slid the same samples for 1 meter of displacement before running these velocity steps. So we have localization within the gouge. Before I showed you just rock on rock. We get more persistent weakening, but as you can see here, this is for 30 seconds at 2.5 millimeters per second. So more persistent, but at a slower rate. We're only weakening 37%, whereas before we reached up to 50%. Going faster, we only get 50%, or about 15 seconds before we kind of start to strengthen the fault. And when we compare the two, when we get an estimate from our data for the parameter, the pressurization factor, we see first of all the gouge-filled faults have a much lower pressurization factor of 0.1 MPa per degree C, whereas the low displacement ones has a 10 times higher, 30 times higher factor, and that really tells you that there's a difference between them, in terms of the pore elastic behavior of these fault zones. If we just see what controls this parameter lambda, we have the thermal expansivity of the fluid. You can disregard this parameter because it's so much smaller than this one, and fluid compressibility and the pore space compressibility. And these two would be equal, would be the same for both type of fault because they are fluid properties, whereas the compressibility would be higher for the gouge can kind of think of it that the gouge is easier to, it's more squishy, it's easier to compress the pore space, but they're also better, they can handle any strains better than just the pore space in the rocks themselves. And this is really the difference between the two. I'm just going to go, hopefully not too quickly, about trying to arrest thermopressurization. So I show you that cracking can do that. We're not certain that we can, that's actually what works, what happens there. We need to get some better idea of if that can happen. And another idea is that can dilation or transient dilation stop thermopressurization. Going back to Rice's equations, this is the general form. I highlighted all the parameters that if we think that they are variables and not constants, then all of these parameters would stay within their spatial derivatives, and then we have to solve it numerically. Rice assumes they're all constant in this model, and you can get an analytical solution. And we can see if we compare the two models to our data, it's not perfect, but we can get a better idea that Rice's model assumes that everything is constant around the fault, and we can continuously, whereas our model shows that we need to start cracking and changing the diffusivity around the faults that in order to stop thermopressurization, as our experimental data shows. Just a quick note about transient dilation. Can that stop thermopressurization? Oh, sorry. Usually when there's a change in velocity, there's some transient dilation. The fault opens up, and we want to see if we can open it up enough to cause the thermopressurization to stop. We just take our experimental data, we change our displacement to strains through a calculation. We can get a strain rate, plug it into the first model that I showed you, the general form of the equations, and just do some forward modeling. And you can see that the black curve shows no dilation, no transient dilation, and the orange curve shows a strain rate of 15 per second. And what we see is that we can only slow down thermopressurization within these forward models and not stop it completely, not arrest it. Temperature rise still increases, and that's just what drives continued pressurization of the pore fluids. So this is a forward modeling. We don't have any experimental data from this. So just to sum things up, I showed you laboratory experiments in low porosity, low permeability diabase rocks that we activated TP at subseismic slip rates. And this is a key point because we use very modest slip rates of millimeters per second. And we know earthquakes can go much faster than that. This, to me, implies that thermopressurization may be activated even at pretty early during an earthquake, where we're still not slipping super fast, and maybe also important in slow slip events in earthquakes if the conditions are impermeable enough. We get some estimates of the pressurization factor. I showed you why it's different from gouge fill and still localized to the bare rock surfaces. And I showed you that in our experiments, opening of fractures helped us to arrest or slow down thermopressurization. Transient dilation from our models did not show that, which leads us to a general idea that we haven't tested yet, is that if transient dilation cannot stop thermopressurization, cracks can, but perhaps persistent dilation can stop thermopressurization. And such persistent dilation can occur if we start thinking about fault roughness. As the fault displaces more and more, there's a bigger mismatch between the two fault planes. They open up when the asperities climb over each other. We open up space for pore fluids flow into, and we can stop thermal pressurization. Okay, thanks so much for listening. Hope I didn't go too much over time.
Thank you, Mil, for the lucid presentation, and we're open for questions. Please.
Yeah, can you go to the slide controlling permeability? Yeah. So what makes you choose these temperatures? Do you do it for an apiary to get a particular permeability, or is it informed by some kind of temperature gradient based on the ambient normal stress of the experiment?
No, we just put the samples within the furnace, we heat it up. There's a paper, the people that pioneered this idea of changing the permeability through subcritical crack growth. This is this paper from '86. It has showed that in these crystalline rocks, when you go to higher temperatures, it depends on the materials. Then because the different grains have different thermal expansivities.
So you do it just to get different permeability?
Yes, yes. We don't go higher. You can go higher than that and just increase the permeability, but we don't want to go. But yeah, you can just control the permeability through that.
During the whole slide, you keep this temperature constant?
Oh, this is just before the experiment. We don't do these experiments at these temperatures.
Okay, so don't you
I wasn't clear about that.
The arrest of the thermal pressurization maybe occurs because the sample is losing temperature?
I'm sorry. Oh no. I wasn't clear about that. I apologize. This is we control permeability of the samples during the sample preparation. I apologize for not being clear about that. We let them, we heat them up for an hour or 3 hours or 4 hours, whatever we want. We let them cool down to room temperature, and then we proceed with putting them within the sample holders and into the rig itself. Okay. No, these are not due to cooling off of the residual temperature in the rig. No, it's not that.
And regarding the arrest of the thermal pressurization, can you go to the slide with the gouge?
Yes.
There is arrest here too.
There's what?
There is arrest of the thermal pressurization here too.
I'm sorry, I didn't.
The thermal pressurization even dies down here too. No cracks here. So how do you?
So, just because it's the gouge doesn't mean there's no cracks. The other thing is that you have within the gouge layer, it's a little more complex because you can localize within the gouge, but you can also delocalize within the gouge. So that also adds another layer of complexity. You can still form cracks, but it's a thin layer, so you're still affected by the rocks that are sandwiched the gouge itself. So we're not out of the woods but being completely sealed from any cracking around the fault here too. Yeah, there's a more recent experimental work from I think De Toro, and they showed with their sealed faults that they are able to get better, more persistent pressurization within their fine-grained gouge experiments. Yeah.
Just a small question. The red lines in all these graphs, are those displacement per unit time or cumulative?
No, it's per unit time. We monitor it. We monitor.
So it's micrometers per whatever microsecond or something.
Yeah, we monitor it continuously. I didn't add this in this plot, but in the space in between here, there's an LVDT that sits. It's attached to the bottom sample. The top sample is stationary, so the top sample just. So the LVDT is attached to the bottom sample, and any relative movements in the vertical direction is just monitored by this LVDT. It basically sits over here. So it's just an analog. It's not analog from when we change it to the system, but yeah, we monitor it continuously.
Yeah, but what you report is actually the dilation.
Yeah, but it's a direct measurement. It's I don't do anything. Yes, it's not exactly here. I don't have a gauge here. Yes.
Two technical questions. Nice stuff. It's not one question, but you mentioned, the displacement you measure. Can you relate it to the thermal expansion of the fluid? Can you try to relate the normal displacement of the fault to properties that you know? That's the mechanism behind thermal pressurization, right? So you should be able to directly measure, or at least estimate how much dilation you should have.
It's hard to say. We're going into like a guessing game at this point because we don't know exactly. We know exactly how the sample holders, how much they open up or close up, but we're still forming some gouge, and we don't have enough constraints of what happens on the fault itself.
Even an estimate
And
whether it makes sense the displacement that you're measuring relative to what you would expect, and you can estimate the properties of the holders.
No, I mean we did some thermal modeling. We only have an estimate of like the temperature from a thermocouple we stuck into one of the samples, but still we have some uncertainty there because we reached up to 60 degrees C, so we don't exactly know what the temperature is, and we don't exactly know what the pore pressures are on the fault. We know the pore pressure is over here because of the low permeability of the sample. So we didn't try that. We kind of felt that we had a lot of unknowns of how the sample actually works in there.
Also, the cooling rate or the strengthening rate, you should be able to connect it to the permeability of the rock samples.
Yeah.
Quantitatively, not just higher or lower.
Yeah. We haven't tried that. No.
Another question beyond technical is okay. I understand it's more difficult to measure the experiment when you undergo phase transition to creation of vapor. But what happens when you do that? What do you see?
We've done some modeling work on that, and there are some experiments that I mentioned that they got that phase transition. What they find is that you can pressurize, change the temperature, and I think they did that in the triax, and they were able to pressurize fluid, but once you reach a gaseous state, the gas itself is so much more compressible. So you can keep the gas pressurized, but it's harder and harder to further pressurize the gas, even as temperature increases.
So that would give you a direct measure of the temperature you see in your experiment, though.
What?
If you see, you just have to translate the system faster, and you get to the point where you start to get the phase transition.
Well, in our experiments, no, because we wouldn't go through that transition.
Yeah, but I'm saying I'm asking why not.
Well,
You could do it.
Well, I don't have the phase diagram for water right now, but it's just for above that temperature, we would still above that boiling temperature, we would still be in liquid state. We would go into vapor. The next critical point would just be the critical point at 374 degrees, and that would just mean that then we have supercritical fluid.
What would that do to the frictional resistance?
So it's a question that I asked myself too, but we didn't get any experiments done just because we couldn't reach those temperatures. We couldn't slide very fast with that setup. And what I found from the modeling that I did is that it's you can still pressurize. But it's getting hard and hard to pressurize. Basically, you can keep the pore pressures high enough. You have to take into account the varying water properties, and but it's getting harder and harder to pressurize fluids. Basically,
But wouldn't
let me just.
wouldn't that mean that would be a mechanism to stop her?
This is pressure. This is like it's from our models, and the pressurization factor. It's more. It's basically at higher temperature controlled by the fluid properties, and not from not so much from the pore space properties. You can see that when we do this at different pressures, the pore pressure over normal stress, we don't have a lot of effect. We do see that the temperature, as temperature increases, pressurization factor drops, and drops by considerably. So it's harder and harder to press. It just makes it's inefficient. You can't. It's harder and harder to pressurize. So that kills. That can kill off.
Problem that you want to solve.
That can kill off.
An earthquake, and you want to understand why it runs away or not.
Mhm.
And okay, the Earth doesn't have any problem moving faster than 2.5 millimeters a second. It would cause, I would guess, this transition to take place. What would the effect be? So I guess maybe you can't do it in your experiment, but and that causes the fault to be stronger or weaker.
Oh, it would just make it. It would make it stronger.
So
There's
then
this.
that would stop that would tend to stop an earthquake.
I thought so too, but there's a problem because as you go deeper into the Earth and higher temperatures, well, it's hard to reach these temperatures because if you have thermal pressurization, it buffers the temperature rise. But if you start your earthquake at deeper, at higher pressures and higher temperatures, then maybe you can cross that critical temperature. But even though it's harder to pressurize the fluid, it's also easier to keep the fluid within the fault zone because the permeability decreases as you go deeper, fewer cracks, the pore spaces become smaller and smaller. So if you have a fault, there's thermal pressurization, it kind of works together. They kind of work together. It's harder to pressurize, but on the other hand, it's easier to keep those pore pressures within the fault zone.
So in other words, some say this, some say no.
Oh, it's still it's calculations. It's whether they're valid or not. It's going into speculations. You can try to do these experiments where we get some stick slip at very high pressures and maybe get these small TP events at these conditions. But again, it's usually the experimental setups are not designed for these types of experiments, so it's hard to get, but it's possible.
Okay, let's close it.
Thank you.